Hello everyone. In previous video, we have already discussed this CMOS construction, and we were discussing upon why PMOS is used as a pull-up network and why NMOS is used as a pull-down network. And so these two questions were there, and we have clearly answered our first question, like why NMOS is used as a pull down network, and this load capacitor is very important. So reference to that only, we are seeing the cases of charging and discharging of that capacitor, and we are doing some analysis. So this was a case of a discharging. You can see that this for NMOS, and this is for charging. Okay, so when there is a discharging, we connect like this. When there is a discharging, we provide a path, like VDD will be there, our capacitor will be charged, and then after a good explanation, we reach to our conclusion. Okay, we reach to our conclusion, like up to this voltage load capacitor can be charged, it cannot be fully charged. So continuing this video, what we are going to do is we are going to discuss like why PMOS is used as a pull down network. Okay, so we have successfully answered for NMOS. Now we will go for PMOS. So here PMOS is used. See, here PMOS is used, and PMOS is used like this. Okay, and here is my capacitor. So what is happening like this? So if I focus on this circuit, why this is connected in this only way only? So this should be my question, and if this is clear, then I'm ready to answer this question, like after doing the analysis. So analysis is done in two parts. Okay, analysis is this is solution number 2, or what you can say is uh, you can say uh, why PMOS is used as PUN. PUN is pull-up network. Okay, you already know. So to answer this, let's make it structure, and let be very clear how to do this. So I'm just making a construction for PMOS. Okay, so this is my PMOS, and I am going to see case 1. And what is this case? Case is for charging. Okay, let's see, is there any problem in charging, or there is some limitations. It will be clear after when I uh, explain you this concept properly. So this is my NMOS, PMOS, and I am going to connect a load capacitor over here like this. So this is my load capacitor. Here would be my VDD. Okay, this is my gate, and you know what is drain, what is source. Yeah, so just you can watch uh, my previous video. Okay, there I have successfully we have successfully discussed and analyzed also, like how to decide what is drain and what is source. Okay, so let's suppose I am applying my instantaneous voltage. Like for all cases my PMOS should be on, so for that I have to apply a 0 volt at gate. Okay, so let's suppose initially it was off, but now after t is equals to 0, my gate voltage is 0. So what does this mean? It simply means like my PMOS is on. Okay, if my PMOS is on, then current is going to flow from VDD to this capacitor. Okay, and Let's suppose the initial voltage for this capacitor was what? Vc of 0 minus. Like before time t is equals to 0, my capacitor was uncharged. So it was having 0 voltage. Okay. Now, after connecting in this way, my load capacitor will start charging because current is flowing. Okay. There is some current, and then that current is flowing here, and now capacitor will start charging. Okay, so let's calculate our boundary conditions. I hope you know what is boundary conditions. If you're not familiar, you can watch my starting videos because these are in the series. If you know the boundary conditions and all, you will not be having any problem. Okay, so for PMOS, okay, for PMOS, uh, what should be my boundary conditions? So my boundary condition is like ki my VSG of t must be greater than V of t. Okay, mod of V of t. So this is my first boundary condition. If this condition is true, then my PMOS is on. Okay, then it could be in linear, it could be in saturation. But if this condition is false, then my PMOS will be in cutoff. So we are not discussing or deciding whether it is in linear or saturation. My main point is it shouldn't be in cutoff. Okay, my PMOS should be on, and this should start charging it. So let's calculate this one. Okay, you know V of t will be 1 for PMOS. So mod of Vt will be 1. Okay, fine. And let's suppose assume we have assumed like my VDD is, let's say, 5 volt. Okay, so it will be easy for us to calculate if we assume some values. So let's solve this. So Vs of t minus Vg of t, and here it is V of t. We don't know which inequality will come here. Okay, if this is come, then it is true. So let's suppose, what is Vs of t? So this is basically source. Okay, so we will go to the source one. Okay, so this is my source, and on my source VDD is applied. Okay, so on my source VDD is applied. So if VDD is applied, then at any point of time, let's say t is equals to 0 to t is equals to infinite, VDD is fixed. Okay, VDD is fixed. So Vs of t at any point of time, its value will be equal to VDD. Fine. Now at Vg of t at gate voltage, what is its value? So you can see its value is 0. Okay, after t is equals to 0 or t greater than equal to 0, my value at gate is what? It's 0. So Vg of t will be 0 forever. Okay, no matter what is time. If time is greater than equal to 0, then my Vg of t is 0. I hope you got my point. So Vg of t will be 0, and V t ka mod, what will its be value? 1. Now tell me, VDD is 5. We have already assumed 5 minus 0, 1. Which inequality should come here? Yeah, tell me. This means this value is greater than right hand side value, and this signifies that my inequality is satisfying. Okay, so there is no point that my PMOS should have some limitation in charging this capacitor. Okay, so there is no limitations. Okay, my capacitor will start charging as soon as current flows. my capacitor would start charging as soon as this current flows, and current will be increased. Okay, current will be increased, my voltage will be increased, and some point of time my capacitor voltage would start opposing the flow of current, but still capacitor will charge. Okay, so current will decrease. Okay, voltage will increase but current will decrease, and at t is equals to infinite, what will happen, my current will be zero in capacitor and my voltage will be vdt. So there is no problem in charging of capacitor, load capacitor, in PMOS, through PMOS. So that's why we use this. Okay, that's why we use this. So you can write here like you can write like load capacitor will be charged to VDD. Okay, and there is rail to rail connection. What is this rail to rail means? Rail to rail means कि this is acting as a switch. So as soon as this is closed, my rail to rail is connected. Like VDD and ground are connected, and in between that my capacitor is there. So my capacitor will charge to VDD. So this is what I mean by rail to rail. Okay, fine. Okay, so we can say like my PMOS can be used for charging. Okay, fine, there is no problem. Now let's discuss for case 2. Okay, what will happen if we are doing discharging of my load capacitor using PMOS? Then what will happen? So let's again make the circuit. This is my PMOS, and there is a charged capacitor. Okay, there is a charged capacitor. Capacitor is now initially charged, and then I have to discharge it. So how should I write in equation form or mathematical form? So my VC at 0 minus is VDD. Okay, so at time is equal, you can write like VC 0 plus also. Like at time is equals to 0, my capacitor is load capacitor is charged, fully charged. Let's suppose its voltage is VDD, and now I have to discharge my capacitor through my PMOS. So what will happen? A current will start flowing like this, and my capacitor will start discharging. Okay, and when this capacitor will start charging, when we provide a path, okay, when this PMOS will be on, then only it will provide a path. When my PMOS will be on, then it will provide a path. So this is on, then my current will start flowing from capacitor as my capacitor is charged. This is higher potential, this is a low potential, and we know that current is flows from high potential to low potential. Only condition is my PMOS should be on. So for this PMOS should be on, we again come to the boundary condition that my VGS of T, sorry, VSSG, because yeah, so VGS is in NMOS we have studied for. So only you have to remember only one thing, and rest it will be opposite. And this all concept has been cleared in my earlier videos. If you wanted to see, you can watch. And for better understanding, you can watch at 2x. I hope. Okay, so let's move ahead. So for boundary condition, as I already mention over here. Same thing I would like to mention. Okay, same thing I would like to mention, because this is same. Okay, so here this condition again should be true for PMOS. Okay, now let's check, and I have to apply one thing here. For PMOS to be on, I have to apply this one also, because we know that when we apply 0 at the gate, then my PMOS get on. So at gate I have to apply this voltage. Okay, this voltage is applied over here. So this is my gate, this is my source, and this is the drain. Fine. So at t is equals to 0 or t greater than equal to 0, my voltage here is 0, so my PMOS will be on. Okay, fine. Now let's do analysis. Okay, let's see whether my PMOS will be on or off, or what the condition would be there. So Vs of t minus Vg of t, you have to break down only, and we already see like mod Vt is what, 1. Okay, mod Vt is 1, or you can just take it as a mod Vt. It won't cause any problem. Can you tell me what is the voltage as source? VDD? No, absolutely not. Like, yeah, it is connected to VDD, but this voltage is varying. Okay, this voltage is varying. Initially, source voltage is at t is equals to 0, it is VDD, but when we talk about t is equals to 1 second or 2 second or 5 second, so it will not be same as VDD. Okay, this will be less than VDD, so this voltage will actually decreases, because capacitor is discharging, so its voltage will also drop out. Okay, fine. So can we write like ki this voltage will be V capacitor of VC, matlab VC capacitor at time t, so that will be beneficial for us. And gate voltage will be what, 0, because I have applied 0 voltage for this PMOS to be on, and this should be greater than mod of Vt. Okay, so there is a condition came that when Vc of t, when Vc of t is greater than Vt, V threshold, then only my discharging will take place. So suppose, let me explain here, कि my Vc of t was VDD, and this VDD is always greater than Vt, then what will happen? This is 5 volt, and let's say Vt is 1 volt, as I have already told. This condition is holding true, my capacitor will discharge. Okay, my capacitor will discharge. Fine, good. If VDD is like 3 volt, if Vc of t is comes to 3 volt, then also it is greater than 1 volt. It is greater than my Vt. Then capacitor will discharge. No problem. Okay, capacitor discharge. But what if my this voltage becomes 0.9? If my Vc of t becomes 0.9, and here this is my V of t, this is my V of t, and this is my Vc of t. So is this inequality holding true? No, this inequality is not holding true, and what will happen? My capacitor will not discharge. My capacitor will not discharge. So by this condition, what I try to explain is there are some limitations. Okay, and that limitation is you cannot discharge my load capacitor below Vt. Okay, as soon as it goes less than Vt, so Vt greater than Vt or there is some low value, this inequality will not hold true. Okay, so this is the concept which I wanted to explain you. I hope this is very much clear to you. So if I am writing my conclusion, if I want to write my conclusion, then I can easily write that PMOS is good for charging of capacitor, bracket में I write like load capacitor, and it will not be used as discharging. Okay, discharging, as it does not completely discharge capacitor. Okay, now you will find interesting to know that what we are going to use. We are going to use PMOS for charging load capacitor. Okay, so if I am making circuit like this, so I wanted to charge the load capacitor. So you already know like how to draw the circuit for charging capacitor. Okay, so like this. Okay, and when I will use NMOS, discharging the capacitor. For discharging the load capacitor. And how to discharge that? Simply we will make NMOS and okay, this will be my ground, this is my NMOS, and this is my load capacitor. So when we do the construction of CMOS, we will combine these two circuits. Okay, and after combining these two circuits, what we will make, let's try to see. Let me copy this circuit. Okay, fine. So here two times I have mentioned this load capacitor, only single time we need to mention it. So can you see this whole circuit? What I have done is, I have done only take this circuit, I have take this circuit, this was PMOS circuit used for charging the capacitor, and we already discussed why PMOS will be only used for charging load capacitor, why NMOS will be only used for discharging the load capacitor. We have done all this analysis. Okay, we have already done all this analysis, and then we are reaching at a conclusion that yeah, so in this manner they should be connected. Okay, in this manner they should be connected. Okay, and then we will simply connect. We say that this is my V in, and here I am going to take my V out, and this circuit is nothing but this is my CMOS inverter. This is my CMOS inverter. So I know this is little bit lengthy, but if you invest this much of time and your concept is getting clear about how the construction is getting placed, and how, what is the role of NMOS, what is the role of PMOS, why I've used PMOS only for charging, it is charging like this, current is flowing, why NMOS is used for discharging of this capacitor like this, then your concept will be much clear and you will feel the concept. Okay, this is all about construction of CMOS inverter, and we have already made a lots of discussion. If you like this video, you can share with your batchmates or colleagues or anyone who can make sure that he can revise these important concepts before going to interview. Thank you very much. Thank you all.